So now we're going to have a look at hypothesis testing when we have contingency tables. Now these tests are called the chi-squared test. This curvy x here is called chi. And when you're drawing your x, it's usual to do the flicky bit first and then the straight line. I know that some people struggle with writing it down. You need to make sure that it looks like a chi and not just a capital X when you draw it. So contingency tables are two-way tables, which hopefully you've seen at GCSE. And usually they are showing the distribution between two different variables, where we've got categories. And we're trying to tell if there is an association between the two variables that we are looking at. So again, we are going to use our formula booklet to get our critical values. And this time it is on page 20 in the formula booklet. And again, just like I have in other sections, I've added a little snippet here of what the critical value table looks like. Now you'll notice how it's split into two sides like this. Now most of the time when we perform a hypothesis test, we are going to use the right hand side of the table. We hardly ever use this side of the table. I am just going to cross it out for now just so you know which side I'm on about. So this side we're going to use quite a lot. We're not going to use this side. The reason for that being is that this side here, it's like we're trying to tell if the data is too perfect for what we're looking at. And here we're trying to tell if the relationship between the values is higher than these values here, then we have something going on in the background that means that the two variables are affecting each other. So that means that we found an association between them. So the first test, we need to find the expected values for our outcome and the degrees of freedom. So we can see here, we've got this little V bit here. That means degrees of freedom. Oops, run out of room a little bit there. And each value from our table is going to give us a contribution. So that's this bit here I'm just reading out here. A contribution to the chi-squared value. And what that means, and you'll see in a moment, the way that we work the value out using our graphical calculator, we have some contributions and those contributions add up to the chi-squared value. Now, if you don't have a graphical calculator, then unfortunately you're going to have to find the contributions first and work backwards from that to find the chi-squared value. And to do that, you need to use the formula, which is on page 6, which is the sum of the OI minus EI squared over EI. Because we have the graphical calculator, we don't need to worry about using this. The graphical calculator is going to do that for us. So because we're using the graphical calculator, all of this can be found in the statistics part of our calculator. And we're going to be using test. So it's a new part of the calculator that we haven't used before. Test, chi. And to start off with, we're going to be looking at two-way. This bit here we're going to talk about later, but for now we're going to have a look at two-way. And because we're using the graphical calculator to do this, we also automatically get our expected values. And we'll also be told from our graphical calculator, because we're using the two-way function, what the degrees of freedom are. Now again, if you don't have a graphical calculators, to find the degrees of freedom, and sometimes you'll need to know this for if the question is just asking a theoretical probability and you can't actually put it into your calculator, then the degrees of freedom is found by doing the number of rows minus 1 times the number of columns minus 1 from the contingency table. So I'm going to have a look at an example. So here we've got a student observed snails on a bare limestone pavement and nearby limestone woodland. The colour of each snail was classified as light, medium or dark. The following contingency table shows the number of snails observed in each category, and this table is called our observed frequencies. So you can see here that we're showing two different bits of information. We're showing the colour category of each of the snails, and at the same time we're having a look at where the snail was found. And we're trying to test at a 10% significance level whether there is an association between the colour of snail and where the snail was found. And as always with hypothesis tests, we're going to start off by having a H0 and a H1. With this hypothesis test, this is one of the only hypothesis tests where we have to use words. So our H0 is going to always be there exists no association between, and then we have to put the two variables that we have. So in this case we have colour of snail and location found. And our H1, our alternate hypothesis, is going to be that there exists an association between colour of snail and location found. Now, some people prefer to write about independence and dependence. No association is saying that they are independent, and an association means that they are dependent. So you may have seen it like this in some textbooks. So now, as I stated before, we need to find our expected values table. I just want to come back so I can show you again how to get to this bit. We're going to test chi, and we're using a contingency table, so we're using a two-way table, so we go into two-way. And then we need to go to this bit here where it's got the arrow mat. Okay, not this one here, but this one here, because this one here is going to change the matrix that these two are looking at, which we don't want to do. Arrow mat is where we're going to put our data in. So we go into this, and then we need to put this two-way table into this bit here. Now you can just start typing the dimensions that you want it to be in, or you can go to this bit here where it says dim, that's the dimensions. And we've got M and N. M is the number of rows that we have, and N is the number of columns we have. So we want it to be 2 because we have 2 rows, and then 3 because we have 3 columns. Now if you forgot which way around that is, so I'm just going to put them in the wrong way around for now, just so you can see what happens. So if I had 3, 2, you can see that this table here doesn't look the same as this table here. So you would have known that you've done something wrong. So if you click exit, it comes back out. If I put them back in the correct way around, number of rows 2, number of columns 3. Now that does look like the table that we have in front of us. So it's okay if you forget which way around they go. Type them in one way. If it doesn't look right, type them in the other way. Now we're going to enter in the values that are in the table. As we do this, so 22 is the first one for light and pavement. You can see that it moves across. So next we're going to put in medium and pavement, which is 10, and then 3 for dark and pavement, 8 for woodland and light, 10 for medium and woodland, and 12 for dark and woodland. Then we want to come back out of this, so we have to click exit, and we want to come back out of this as well, so we need to click exit again. And then we need to click execute. So what that's going to do is it's going to have a look at this table for us and tell us the important bits of information. So there you can see that we've found some data. We don't write that down straight away. We are going to eventually write this down. And we're going to come on to later why we don't write this down straight away. But first of all, we need to click on this arrow mat button again. And you can see now that not only has matrix A got some data in it, but also matrix B does. If I just go back far enough, the reason for that is we typed in our observed values into matrix A, and what the calculator does is that it fills matrix B with our expected values. And as I've said in the explanation, we need to know what those expected values are. So just going back to that bit, arrow mat, and then we're going to go down to matrix B, and we need to write down these values. So in a separate table, I'm just quickly going to draw one here. Whoops. There we go. There we go. So we don't have to write down the whole words. P and W will be fine for pavement and woodland. Light, medium, dark are fine for the top bits. So then we've got 16.2. Remember to write things to at least 3 significant figures. 10.8. 8.08. 13.8. 9.23. And then 6.923. Sorry, I should have just put 6.92 there. There we go. And remember, as I've just said, this is our expected values. So, if the location of the snails was completely random and they didn't have anything to do with what colour they were or what location they would be found in, we would expect to have the numbers that we found distributed like this. This is what we were expecting to find, and this is what we actually found. And if you wanted to, you could have a quick look between them to see what kind of things you could notice. For instance, medium had 10 and 10. Here it says 10.8 and 9.23. So they are quite close to 10 and 10. However, if we have a look here, we only found 3 dark pavement ones, but we were expecting to find 8.08, so that is something that's a bit different. And again, for the dark and woodlands, we're expecting much less than what we found here. So that's just a couple of comments that I'm making, having a look. I'm not writing any of this down, this isn't part of the answer, but it's getting you used to what this table actually means. This is the number that we were expecting to find. These are the numbers that we actually found. So I'm going to come back out of this. Exit, exit. And now I'm going to actually write down these values that I have here. So the chi-squared value is 11.6. That is our test statistic. Then we need to write down the degrees of freedom. As I said before, it's here in our calculator, so our degrees of freedom is 2. But also remember, if you're not using the graphical calculator, you would do the number of rows minus 1. So we have 2 rows, 2 minus 1 gives us 1, times the number of columns minus 1. We have 3 columns, 3 minus 1 is 2, and then 1 times 2 gives us 2. So that's where the degrees of freedom being 2 has come from. So now we need to have a look in our formula booklet at the critical value. As I said, we're going to use the right hand side. We have 2 degrees of freedom and we have a 10% significance level. Now we always treat this as being one-tailed, meaning that we don't halve the significance level for anything. And that's quite important, that, because all these tests that we do to do with chi-squared, we're always just going to use the significance level that's given to us in the question to have a look at our critical value. So you need to be careful with that. We're always treating it, there's only one way that we do this test, which is no association, or that they're being independent, or an association and they're being dependent. So we don't do anything with the significance level, we just use it straight from the question. So in this case it's 10%. So if I come back up here, you'll notice there is no 10%, and that's because we need to think of it the other side of it, because we're looking for the numbers to be not in line with each other. So 100% take off 10% gives us 90%, which is 0.9. We have 2 degrees of freedom, so going across from 2 to 0.9 gives us 4.605. So the critical value is 4.605. So that means that these numbers here are more different to these numbers here than we would like, because this is what this is. The test statistic is having a look at the contributions of all the differences between the expected and the observed values. If it ends up being less than the critical value, then it could have just happened by chance, but here it's more than the critical value. So that means that as the test statistic is bigger than the critical value, we are going to reject H0. There is a difference at a 10% significance level. There is sufficient evidence to suggest, and remember that we write about H1, so an association between colour of snail and location found. So that's just part A. I'm just going to extend the page rather than going on to the next one, just because then I can keep the question on here. So having a look at B, we're asked where are light coloured snails more likely to be found. Well, we have found more light coloured snails on the pavement than in the woodlands, so I would say pavement from that. So on the pavement. However, if we have a look at part C, it says give a reason why the location where most light coloured snails were found may not be the place where light coloured snails are most likely to be found. This is quite a difficult question to answer. Something that can help us to do this is having a look at the contributions. Now, if you did it the non-graphical calculator way, so using the formula here, the individual values of this before you add them up are your contributions. However, we can use the graphical calculator to help us to get these. What we have to do is we have to type in our observed values into list 1. I'm going to do this going across. Whichever way you decide to do this, you need to also then type your expected values into list 2 in the same way. So into list 1 we're going to have 22, 10, 3, that's working across, then 8, 10, 12. Then in list 2, so they were my observed values from this table here. Then in list 2, I'm going to type my expected values in, and I need to do that in the same order I just did. So working across the top, I'd have 16.2, 10.8, 8.08. Then working along the second row, 13.8, 9.23, and then 6.92. Just quickly double check that you've typed everything in correctly again. You don't want to have typed something in wrong. Just checking my observed values again. Then we're going to test chi, and this time instead of going into two-way, we're going to go into this button here. Now GOF or GOF means goodness of fit, so it's having a look at the contributions to the chi-squared statistic. So we click on that, and you can see here, did we type our observed values into list 1? Yes, we did. Did we type our expected values into list 2? Yes, we did. And that's a way that you can remember which way to type them in. If you go into that bit, test, chi, gof, have a look. Right, I need to type my observed values into list 1. I need to type my expected values into list 2. And then you can see the degrees of freedom. Yes, it was 2. If that's not there, then you need to type it in. Remember, it's the number of rows minus 1 times the number of columns minus 1. And you need this centerb bit, centerb, to say list 3. Now that's quite important because when I click X now, there we go. We were hoping to get a chi-squared value that was almost exactly the same as what we ended up with before. And it pretty much is. Look, 11.56, which would round to 11.6. However, now, when I come out of this, so when I click exit, exit, you can see that list 3 here has been completely filled out for us. So these are our contributions. We need to write these down and we need to make it clear which one is for which piece of data. So I'm going to do this in a table. You could do it in a list and make it clear next to each one what each one is standing for. So these are our contributions. So pavement, woodlands, light, medium, dark. So we've got 2.08, 0.0592, 3.1938, then working across the second row, 2.44, 0.0642 and 3.73. And hopefully if you did it the other way, then you would have started off with these values. If I just go into the normal part of my calculator and add these values up, so 2.08, plus 0.0592 plus 3.1938 plus 2.44 plus 0.0642 plus 3.73. There we go, and we end up with 11.6 again, rounded to 3 significant figures. So you can see that these contributions here, when we add them up, they give us our chi-squared value. So when we have a look at this, we can see where each set of data contributed to our chi-squared value. Just to point out some of the bits I was talking about before, you can see here that the smallest contributions are these medium ones here, which is what I was pointing out before, that 10.8 is quite close to 10 and 9.23 is also close to 10. So we weren't expecting those to give us a big contribution because they weren't really being altered. However, if we have a look here at the dark ones, they are the biggest contributors. And that was me pointing out that 8.08 is a lot more than the 3 than we actually found. And we were expecting to find 6.92 dark in the woodlands, but we found a lot more than that in reality. So when we're writing a statement now, it's a good idea to try and bring up those two. So remember that we're trying to explain why the location that we find the most light ones might not necessarily be the place where we were expecting to find the most light ones. So there were a lot. Sorry, try and write it a bit better than that. So we found a higher number of dark coloured snails in the woodland than we were expecting. So we found 12, we were expecting 6.92. So how could this have helped us with the light ones? Well, this may have meant that we didn't see as many light coloured ones as our count was taken up by the dark coloured snails and conversely, talking about our dark coloured ones on the pavement, we found a smaller number than we were expecting of the dark coloured snails on the pavement. So we were expecting, we actually found 3, three. And we were expecting to find 8.08. So this may have led us to find more light coloured snails. So you can see there how the contributions helped us to see things that had been altered due to having a look at the contributions. Now, usually, whenever you have to talk about the contributions, we usually select the two biggest numbers, which in this case is dark and pavement and dark and woodland, which is what I've talked about here. So if you're asked about the contributions, we usually talk about the two biggest ones. I only highlighted the two smaller ones before because those were the ones that I'd talked about previously and they ended up being the smallest contributions. So I'd like you to pause the video now and give the Now You Try a go. Remember to be careful when you're putting this originally into your calculator. We're going into test, chi, two-way, because we want to put the two-way table in. So pause the video now and give this question a go. So hopefully you've paused the video and given the Now You Try a go. For the first bit, we're testing a 5% significance level, whether the grades obtained are independent of the school. I've written the hypothesis in terms of association, so no association and association. If you did it in terms of independence, it'd be that the school and grades are independent and the school and grades are not independent or are dependent. Then remember, we go into test, chi, two-way, arrow map, this time 2, 4, so you can go into dimensions and put 2, 4, typing in your observed values into there, then coming back out of that, clicking X in, you should have come up with this screen, then going to mat, and then down one. Those are our expected values, which you can see I've written there. You have to write them down, as I explained before. We are going to come back to why we have to write them down later on. And then we come back out of that and we're writing down our chi-squared there, which is our test statistic, our degrees of freedom there, which is 3. Using our critical value table to have a look at our critical value, remembering that this time, because it's 5%, we'll be looking down from 0.95, because remember we do 100% take off 5%, and our degrees of freedom, as we can see here, and I've written it down here, is 3, so we're reading across from 3, which gives us 7.815. And again, as the test statistic is bigger than the critical value, we reject H0 at 5% significance level. There is sufficient evidence to suggest an association between the school and the grades that the pupils got. So then, for the next bit, which school did better, got better results? Well, for this one, I did have a look at my contributions just to check which values were the biggest contributors to our chi-squared statistic. Now, if you did this bit first and then worked out your chi-squared value, it might have come out slightly different. Remember that we do this by typing in our observed values into list 1, our expected values into list 2, and then going into test, chi, and then goodness of fit, making sure that it tells us our degrees of freedom is 3. And you can see there that this time our chi-squared is slightly different, which is why I was just saying that your contributions might have been a little bit different to that. There should have still been that the AB ones were the biggest contributors, and remember that that fills out automatically your list 3 with the contributions that you need to write down. And we can see from this that it was the A, B grades that made the biggest difference. So that means that Gorton, AB, well, we were expecting them to have 10.3, but they actually got 16. So that means that Gorton performed better as they had a higher number of A/B grades than we were expecting. Whereas, if we have a look at Prestbury, we were expecting them to get 13.7, however they only got 8. So that again emphasises that Gorton did better. So give a reason why the school with better results might not be the better school. So this is asking for a real life situation now. So I just put Gorton could have had a stronger cohort to begin with, or pupils which have higher predicted grades than Prestbury. Just because a school has more A or B grades doesn't necessarily mean that it has performed better, because if one school is, let's say, a grammar school, you would be expecting them to get better results because usually they take stronger pupils than the other one. I just want to point out one more thing. If I just go back into where I originally got my chi-squared one from the two-way table, okay, you can see that not only do we have this chi-squared, but we also have a p-value. Now, what that p-value tells us is the probability that we get this number at random. And as you can see here, our p-value is less than 5%. It's 0.04438417. So that means that we would be expecting to reject H0, because remember, when we do a hypothesis test, where we're comparing probabilities or p-values with a significance level, if the probability that we have is smaller than our significance level, then usually we would end up rejecting H0. So you can see here that as a double check as to whether you've done your conclusion right, if you are using the graphical calculator that is, then you can see that was 5% that we were using. The probability of getting 8.08 by chance is 0.0444. So that means that it's less than 5%, so we were expecting to reject H0. So it's just a way that we can use the p-value that comes up in our calculator to help us to double check that we have chosen the correct value from our critical value table. So, another important thing to just point out as well is that when we perform this test, we need to have these values in our table, in our observed values table that we're given at the beginning, to be frequencies. And in the next video, we are going to talk about what we do when they are not frequencies and how we can change that. Thank you very much for listening.